Physicists in the early 20th century thought that all matter was made of electrons orbiting around a nucleus of protons and neutrons, but much was still left unexplained.
For example, in 1912, physicists began detecting cosmic rays from outer space made from otherworldly particles. In order to study them in greater depth, physicists used particle accelerators to recreate the matter from these cosmic rays. This led to a torrent of new particle discoveries and left particle physics with more than 80 supposedly fundamental particles of the universe. There had to be a way to make sense of them and their exotic properties. And indeed there was. American physicist Murray Gell-Mann proposed that protons, neutrons, and all of these new particles were really composed of smaller particles, which he named quarks. The quarks came in 3 varieties. There were the up quark, the down quark, and the strange quark. The quarks also had 3 antimatter analogs called antiquarks. They were the anti-up, the anti-down, and the anti-strange quark. When these quarks were grouped into 2s or 3s, they would form particles known as hadrons, which were what protons, neutrons, and the other new particles were. It turns out hadrons came in 3 different types themselves: mesons, baryons, and antibaryons. Mesons include 1 quark and 1 antiquark. Baryons include 3 quarks, and antibaryons include 3 antiquarks.
Protons and neutrons, for example, are baryons, as they each contain 3 quarks.
The proton contains 2 up quarks and a down quark, and the neutron contains 2 down quarks and an up quark. Murray Gell-Mann's quark model seemed to fix many of the issues with hadrons, including the charge of the neutron. Neutrons were known to have neutral electric charges, but this could only be explained by the quark model. As up quarks have a charge of plus 2/3 and down quarks have a charge of minus 1/3, together the quarks give a neutron a neutral charge. Voila!
Gell-Mann's quark theory became widely celebrated, and much like what Mendeleev's periodic table did for elements, Gell-Mann found an underlying structure for hadrons.
Say you had a pile of apples. They would range from large apples to small apples and sweet apples to sour apples. If we wanted to organize all the different apples, we could plot them on a graph using size and sweetness as the 2 axes.
Gell-Mann applied the same idea to particles, except he used different axes.
On the x-axis, he used a property of hadrons called isospin. Isospin related the number of up and down quarks and antiquarks in a hadron. On the y-axis, he used a property called strangeness, which related the number of strange and anti-strange quarks in a hadron. When all the hadrons were plotted onto their respective graphs, a pattern emerged. Gell-Mann called these different patterns the eightfold way.
Gell-Mann's work with quarks was key to the development of the Standard Model, and it even predicted a new particle which was later discovered. Today, we know of 6 different types of quarks and antiquarks, and our knowledge of these particles is constantly growing. So the next time someone tells you that protons and neutrons are as small as it gets, remind them of the crucial role of our friends, quarks.